So hello everyone again. So we have a new subject which is transient conduction and as well as introduction to convection. Okay. So before starting the conduction problem, we have a question for you. The question is as follows. So we have a figure as shown here. There is a sample and there is a heat transfer through the sample. So the question says, after the sample, when leaving the sample, is this Q dot same or not? Is it more? You should specify it, or less. So why or why not? Explain in not in detailed form, but briefly. Explain briefly that if it is more, why, and if it is less, why. So you have 45 seconds. So I think we can start the time now. You can write your answer as a comment. I will later read the comments and then we will see who has the true answer for the question. Top and the bottom parts are insulated. Okay, so you don't need to consider top and the bottom parts. You have only front and the back side of the sample. You have 20 seconds. You can see the time here. You have 10 seconds. You have 3 seconds. And the time is up. Okay, so firstly, we should see if there is answer about this question, so then we can continue our explanation if there is true answers or not. So we have the comments. Let's see the comments. So it will be less energy loss. It will be less because the sample, less because of energy loss. It is less. It is not same because sample conduction have resistance. Okay, so yes, there are true answers. So the reason is very obvious because you have the sample here. This sample has some internal energy of the U. Okay, internal energy. Okay. So when this Q passes through the sample, some part of the Q becomes internal energy of the sample. And then the other part leaves the sample, Q dot rest. Okay, if you know the first law of thermodynamics, the change of internal energy of the system is into the system minus out of the system. Okay, these are rate quantities. In this case, du by dt is not zero because you can approximate. For example, you say that it is steady system. So if it is not steady, if it is transient, this one is not equal to zero. Okay, therefore, in and the out quantities, so you will have the difference in between them. Okay, therefore you will have less Q dot at the end of the sample because some of the Q dot becomes internal energy of the sample. But if it is steady, say that steady, then du by dt will become zero. If du by dt is zero, it means that the sample has some temperature. That temperature is constant. Okay, the temperature of the sample is not changing. So you can say that it has become saturated. If it was 20 degrees Celsius and increased to 80 degrees Celsius, now it doesn't change its temperature. Therefore, internal energy doesn't change. Whatever comes to the system and that one leaves the system. Therefore, Q dot is same. So if you have approximated steady case, but if you have approximated transient case, you will have less due to energy loss in the system. That energy loss becomes internal energy of the system. So there are true answers, but we will evaluate the answers after the lecture ends. Okay, we have 2 more questions. Now we have the transient conduction. Transient conduction problems can be 0-dimensional. I will say what is 0 dimension here. So it can be 1D, 2D, and the 3D. Okay, so we will not cover this part, and that part, and also this one. Okay, we will only cover the convection dominating transient problems. Okay, and here we say unsteady. Unsteady is exactly the same as transient. Okay, when we say unsteady, it is transient. And 0-dimensional unsteady heat transfer problems, here we will cover only convection dominating case. So heat loss is by convection. There is no radiation heat loss. Okay. This is the simplest form, but it is applied in most of the cases. Okay, it is very general but simple. Good. So what is convection 0 dimension? So this is also called lumped capacitance method. Capacitance method. Why lumped? Because there is a lump of material that you put in fluid. Okay, so lump means a piece of material. So let's see what is lumped capacitance method or zero-dimensional unsteady problem. So I have a sphere here. So it is red color. Red color means everywhere the temperature is the same. So if you take any point on the sphere, it has the same temperature. Okay, so for example, this one, that one, anyway. So I put that sphere into fluid, okay, in the water, for example. And then it has initial temperature of 150 degrees Celsius, and when the time is 0. Or you can say that Ts of the sphere at the beginning time, Ts initial is 150 degrees Celsius. Okay. And you have T infinity around it, because T infinity is the infinity temperature away from the body, or temperature of the fluid. So as time passes, the temperature drops. But we say that temperature drops uniformly. Uniformly, we mean whatever temperature is there, 100 degrees Celsius, that temperature is also here, that temperature is also here. So any point you take, the temperature is same, 100. Okay, so here you see there is no change with respect to location. Therefore, it is, as we have said here, zero-dimensional. There is no dimensionality, but there is only change with respect to time. Okay. So after some time, the temperature drops, but it drops everywhere the same. So this will be the first approximation. First approximation is that temperature drops uniformly in the body. Okay. So the temperature drops uniformly. So and then you have the 70 degrees Celsius temperature, but as we have said, it is same everywhere. Then you have 47 degrees Celsius, and it is same everywhere. So if I have T surface here, which is 47, that T surface is also here 47. Okay, it is uniform temperature drop. Why it is uniform? It is very valid assumption, approximation. Why it is uniform? Because the body itself is very small. So as it is very small, it is lump, a piece of material. It is very small, and therefore the temperature changes at each location at the same time, simultaneously. Okay, therefore, this is the first approximation. Second approximation is that the body is small, as we have said, T infinity is not affected by the temperature change of the body. Therefore, T infinity is constant. Okay, these are two major assumptions in this problem. And we have said here it is dominated by convection. So dominated by convection means that heat loss from the body is by convection. There is no radiation effects. Okay, it is zero-dimensional, no change of temperature with respect to location, and it is transient because the temperature changes with respect to time. As time passes, temperature changes, and also it is convection dominating case because you have heat loss only by convection, CV. Okay, good.
There is no conduction here.
Yes, there is no conduction
Why?
here because the body, you can say that body has very high thermal conductivity, or it has very small resistance. We will prove it. Okay, in the next parts we will prove it. We can say that it has very small resistance with respect to water. I say that RCD of sphere by RCV of fluid is much less than 1. Okay, if it has small resistance, this is your body. Okay, so here it is, for example, 20 degrees Celsius of T infinity. Here, so here you have 20 degrees Celsius of temperature. If it has small resistance, it means that this infinity of 20 degrees Celsius is propagating into the body at a very high speed. So here temperature drops, for example, 100 degrees Celsius, here drops 100 degrees Celsius. So it has very small resistance, therefore this 100 degrees Celsius is felt everywhere at the same time. Understand what I mean? Because it has very small resistance, the body feels it everywhere at the same time due to its small resistance. And then the temperature drops at the surface because firstly, the surface of the body feels the temperature. Okay, here temperature is 70 degrees Celsius at the surface. But since the body has small resistance, all of its locations feel it at the same time. Okay, because
how we know body has small
sorry?
how we know body has small resistance?
Yes, body doesn't have smaller resistance. It has smaller resistance with respect to fluid. Okay, if you compare resistance of the body with the resistance of the fluid, it is very small value. Okay, but if it is copper or if it is aluminum, steel, it doesn't matter. They have the very small resistance with respect to fluid. We neglect it. Okay, this is approximation, but it gives good results. Okay, it gives good results. So if you know quenching, so it is famous application for this lumped capacitance method. So let's analyze what happens. You have the body here, the sphere. If you go back to here, sphere, and around the sphere you have the convection. So if I write the first law says that change of internal energy with respect to time is equal to total in minus total out. Okay. So here the body doesn't have any input. These are rate quantities, by the way. The body doesn't have any in quantity. Okay, this one is 0. And I assume that Ts is greater than T infinity. Okay, T infinity of the fluid. Therefore, body gives off heat, and that heat is by convection. Okay, CV. And the convection heat transfer is HAS Ts minus T infinity. Okay, and we have said Ts is function of time. It changes with respect to time, but that Ts is same as T inside the body. Okay. What I'm saying is that here you have Ts, that Ts is also here Ts, that Ts is also here Ts. Okay, but it is function of time. And the change of internal energy from first law of thermodynamics, you know that we can write it as mCV, the change of temperature with respect to time, because since du is mCV dt, or if you write in finite form, you will have mCV into delta t. Okay, they are the same stuff, but here you have small change in internal energy will be mCV dt, and this is the change of internal energy with respect to time, and this is in quantity 0, and you have the out quantity, which is by convection, and convection is by Newton's law of cooling, H into As into Ts minus T infinity. And we are saying that T infinity is constant. We have said it. H is constant. As is geometry. It is constant. Okay. This is the approximations, and the approximation, we will prove it in the next slide. Okay. First, let's solve this differential equation. So left-hand side, you will have mCV dt by dt, and the right-hand side, you will have HAS Ts minus T infinity. So as I said, T is same as Ts. Therefore, instead of T, I can write Ts. Okay, because change of du by dt is change of temperature of the body. Okay, with respect to time. That body temperature is same as Ts itself, because each of location of the body feels the same temperature. Therefore, Ts is same as T. Yes.
One question.
Yes.
CV is the it is for our material, not for liquid. Yes.
Yes. This is yes. Du by dt is our material. This is material du by dt, and this is yes balanced by CV.
Yes. Okay.
So you will have this differential equation, and I said that T is same as Ts. I have said it because the body has the same temperature everywhere. It doesn't matter it is Ts, it doesn't matter it is T. It has the same temperature everywhere. So I have this differential equation. So what you can do here is that you can write it as dTs. Let me erase this one first. First, our methodology that you will have. You can separate this differential equation and then integrate. Okay. So what you can do is that dTs by Ts minus T infinity will be equal to, we are separating, first we are separating negative HAS by mCV into dt. Okay, this is very simple differential equation. Therefore, we are doing this part. So now H is constant, As is constant, M is constant, CV is constant, and only change Ts. Ts only change, and the time change. Therefore, I can put integration limits as, let's put integration limits. So when T is 0, what is the Ts value? Ts value is Ts initial. So this is specified in the question, or the question asks for it. Then t is t, and the ts is ts. That is simple. Okay. So right hand side is very easy part. Let's do it firstly. MCV into t. And for the right hand side, this is the ln function. Okay, so for this ln function, firstly we should find what is the ln function of this one. So what is the ln function? So say it. What is the integral of dt? Let me write it here. Kopya oldu burada.
Is it question, sir?
No, I'm just asking what is the integral of this one. Yes. In the first case, instead of ts, you will write ds, it is the same. In the second case, you will write ts minus ts initial. Let me write it. So ln, it will be ts minus t infinity. It is the upper bound, and you will write the lower bound. It will be ts initial minus t infinity. Okay, is it okay?
Okay.
Good. And the ln functions are not very common. We convert it into exponential functions. So take exponential of the both sides. If you take it of both sides, and if you take exponential of the both sides, you will have ts minus t infinity. Ts initial minus t infinity will be equal to e to the power of negative has by mcv into t. Okay, so if this part is okay, or you can go on, so you can say that ts is equal to ts initial minus t infinity times e to the power of has by mcv into t plus t infinity. So both of them are okay. So if you stop it here, it is also okay. This is the result, or you can take this one. Okay, both of them are right and common. So this is the result. So if you have a lumped capacitance method, the temperature of the surface or the body changes with respect to time in an exponential manner. We will have questions about this, but firstly, I have a question for you. You will have some time for this question, okay? So let's see the question. What is the unit of HAS rho v Cp? Okay, rho v means this one. Rho v is mass. HAS mCv. So you have 45 seconds. Go on, my friends. So firstly, let's start with H. H has unit of watts by meter square into degree Celsius into AS. AS has unit of meter square. Divide by. Rho V is mass. It has a unit of kilogram. Multiplied with CV. It has a unit of joules by kilograms degree Celsius. Okay, or you can say that CV is to decrease energy, joules required to increase temperature of 1 kilogram of fluid by 1 degree Celsius. Okay. Is a common definition, so let's write it here. And the meter square cancel out, kilograms cancel out, so I can write it as watt by degree Celsius into degree Celsius by joule. Degree Celsius cancel out, joules cancel out, you will have 1 by second. The unit is 1 by second. Let's see if there are new answers. T by T. So what is T by T? T is temperature.
Yes, delta temperature over second. I mistaken somewhere.
Okay, yes, delta degree Celsius should cancel out. Okay, this is 1 by second. So this is the unit of, let me see if you have another slide here, because yes, good. I have one more slide. So why do we need it? So for exponential functions, what we are doing is that, this is very common. So I can write Ts is T infinity plus Ts minus T infinity into e to the power of negative T by tau, where tau is time constant. Okay. For exponential functions, this is the general stuff that we are always doing. What you are doing is that you are dividing the variable, this is time, into the rest of the values, which becomes most of the time constant. Okay. So I will do now. So we have Ts is Ts initial minus T infinity e to the power of T by tau plus T infinity. Okay, so here we have this function. So we will simplify it. Ts minus T infinity divided by Ts initial minus T infinity. And this one will be equal to negative e to the power of T by tau. Okay, we can give a name for this function, which is theta for this function. The name is theta. Okay, So I will plot theta versus time. Okay, let's plot it. So firstly, when t is 0, okay, t is 0, this part is 1, and theta is also 1. Why? Because when t is 0, ts is ts initial. Okay. Therefore, ts initial minus t infinity by ts initial minus t infinity, it makes 1. Therefore, theta is 1. And time is 0, theta is 1. When time is 1 tau, then you will have e to the power of t by tau will be equal to, so if I use my calculator, so when t is 1 tau, you will find exponential of t is 1 tau, this makes negative 1, e to the power of negative 1. So let's do it, e to the power of negative 1. It makes 0.37. So e to the power of negative 1 is 0.37. This is the value of theta. So if it is half, then you will have somewhere around here, 0.37. This is the value of the theta. Now, when t is 2 tau, you will have e to the power of t is 2 tau, you will have e to the power of negative 2, and that value will become, let's find it, the exponential to the power of negative 2. Next, 0.14. 0.14, the half is somewhere around here, so you will have 0.14 here. So let's write the values. This one is for 1 tau, and if I go to the next point, this one is for 2 tau, and then I say that t is equal to 3 tau, you will have e to the power of negative 3 will be equal to, let's find it, so again, exponential of to the power of negative 3. You will have it 0.05. 0.05. So half of it is 0.07. It will be around here. This 3 tau is 0.05. Okay, so I show the dots here, so you will have points like this one. And then if I say that t is equal to 4 tau, you will have e to the power of negative 4. Let's find it. The exponential of negative 4 will be 0.02. Half of it is here, you will have 0.02 here. This one is 4 tau, and you will have the value here. So if I go to 5 tau, you can go 5 tau, you will have, let's do it and finish this part, e is to the power negative 5. The 0.00 is 0.5, 0.007. You see the value drops to very small values. Most of the time we are stopping here, okay, and we say that 3 tau is enough, okay, and this 3 tau means that the system has reached its steady state value. Steady state value, we mean that it doesn't change anymore. It changes, but very small, therefore most of the time we stop at 3 tau. So if you look at here, it means that after 3 tau, the difference between ts and t infinity versus or over the initial difference is very small, okay. Therefore, if you plot the function, you will have something like this one. I plot it. First this part, this part. Okay. This is the plot. So if you go to infinity, it will be asymptotic approach. Good. This is the function of the theta, and this is the time constant of the problem. And this is the time constant of the problem. So the time constant, the shape of the graph depends on the value of the tau. If the tau is very large, let me compare the values for the tau. So this is the profile, this is the theta, sorry, and this one is the time. And theta is ts minus t infinity divided by ts initial minus t infinity. Okay, so you can have different shapes for the temperature change. This is the one possible case. This is another possible case. This is the third possible case. If I make the time axis longer. So what happens is that this one means tau is high. Okay. This one means tau is small. If tau is small, you see that the system gets its state value at a small time value. Okay, so if I do that, so for this curve, the time constant is somewhere around here. Okay, for this one. But for this one, time constant is somewhere around here. You see, this system gets its state value faster than that one. Okay. Therefore, the time constant shows, tau shows, the system shows the response of the system. If tau is large, the system response is too slow. If tau is small, then here system response is small. System response is small. But if tau is small, then system response is high. Right? And this is the meaning of the tau, and this tau is called time constant. We are looking for small tau because the smaller tau means fastest response. Okay, fast response. Okay, small tau means this part should be as large as or as small as possible. So what is the value for the downstairs? Small tau means fast response. Fast response means h will be large. H will be large. AS will be large. Okay. If H is large, AS is large, it means that good heat transfer. Okay. Because if you compare, for example, this is the sphere. Okay. This is small AS, but if you have a larger sphere, okay, large AS, then you have good heat transfer. Okay. This one is good. Good heat transfer. And also H. If H is large, you have better heat transfer. H is large, you have better heat transfer. Okay, therefore it is good. And M should be small as possible because M is thermal inertia. Okay, thermal inertia. Thermal inertia means it is difficult to change the temperature of the body if M is large. Okay. Therefore, M should be MCVM, this one together. Okay, this one is thermal inertia. So if M is large, mass is large, it is difficult to change the temperature of the body. Therefore, M should be very small. CV also should be very small. Okay, thermal inertia means it is difficult to change T of body. Okay, difficulty. Okay, measure of difficulty to change the temperature of the body. So therefore, we want MCV to be small as small as possible. This one should be small as possible. Okay. But we want H and the AS to be large because MCV, if it is small, then it is good transfer heat. If HAS is large, then it is also good for heat transfer. Okay, good. So we have an example here. We will first solve the example and then we can continue. So our example is as follows. Let's go to example. Yes, we have steel rods that are hot and they are wound into coils while ductile and can be used in springs of car suspension system. So you can see these are hot steel rods and they are leaving the oven. Here you have the oven and they are leaving the oven at high temperature. Okay, and then they are converted into springs, and these springs can be modified to be used in suspension systems of the car. And it says that it has a diameter of 2.5 centimeters. So these steel rods have diameter of 2.5 centimeters and the length of 1.27 meters. And oven with a constant heat transfer coefficient is 20. So you have an oven here. So there is an oven. This one is your oven. It is large, but in our case, we can take a small. It has an H of 20. Okay. You have an oven, and this oven transfers heat by fans or whatever you have in the system. So this is 20, And they are used to heat the steel rods from 20 degrees Celsius to 450 degrees Celsius. So it says that what is the temperature inside the oven if 10 minutes is enough to heat the rods to the desired temperature. Okay. So one more time, the question says, what is the T of the oven? Okay. If we need 10 minutes to heat these steel rods to 20 degrees Celsius for under 450. So in other words, you have 10 minutes for finishing this process, heating process. But one more slide here. So, okay. Firstly, we should write the given value. So you have the rho here. First, let's write diameter is 2.5 centimeters. Okay. And you have L of 1.27 meters. And we have H of 20 watts by meter square Kelvin or degrees Celsius, it doesn't matter. So it says that we are heating rod from 20 degrees Celsius to 450. So it means that the initial temperature of the rod is 20 degrees Celsius and it has a temperature at 450 degrees Celsius. This temperature, this one is at when time is 0 and this one is at when time is 10 minutes. Okay. And then, so if you write the equation, so we need T infinity here because T infinity is required to heat these steel rods. Okay, if you write your equation will be Ts will be equal to Ts initial minus T infinity into exponential of negative T by tau plus T infinity. Okay, so these are our differential equation. Okay, this is the differential equation. Now we will solve this. This is the governing equation. Now we solve it and get the values here. Firstly, we should calculate what is tau because tau determines the speed of the system. If tau is very large, it means that it is a lot of time is required to heat the system to the desired temperature. Okay, so let's solve the problem. So we'll use Excel to solve the problem. So I will add one more part here. So I will first start with tau. The tau is, let me write the tau here. Tau values here. So what is tau? MCV by HAS. So let me write the tau here. Tau will be MCV by H into AS. M is rho into V. Okay. So what is the rho? Rho is given 7832. This one is the rho. Into a volume. What is the volume of the cylinder? Volume of the cylinder is cross-sectional area pi the square by 4 into the length L. Okay. This is the volume of the cylinder. And then you will get the answer because D is okay, L is okay, and the M is okay. Then CV value, CV is, let me use another color here. CV value is given in the question, it is 434. This one is CV value. And the H value is also given, it is 20. This one is the H value. And now comes AS value. AS is the surface area of the steel rods. You have the steel rods here. The surface area of a cylinder is the circumference into the length L. So the D is given, that is 2.5 centimeters, and L is also okay. This one is 1.27 meters. Okay, we have found the tau. Now the time T. Okay, the question says when time is 10 minutes. 10 minutes means 10 into 60, 600 seconds. Okay, when time is 600 seconds, you have Ts value of 450 degrees Celsius. Okay, when time is 600 seconds, Ts is 450 degrees Celsius. And initial Ts is 20 degrees Celsius. Okay, then T infinity is under question mark. We should find it. We know the exponential part and we know this. Right, solve it in Excel. Everything is okay. Only unknown is T infinity. Okay, first let's find the mass of rho V. Okay, tau means first we should know mass. To know mass, I should know the density into volume. Therefore, insert for the density part, and the density is 7832. And also I should know the volume. Okay, so first let's write the given values here. We have the diameter. Diameter is 2.5 centimeters. 2.5 e to the negative 2. It means that we have converted into meters. L is 1.27. You have H is 20. You have Ts initial. This one is given. Initial. It is 20 degrees Celsius. Yes, it is given as 450 when time is 10 minutes. Okay, I will write it as time minutes, and I will add time seconds. This one will be, second time will be this one multiplied with 60. Then it will be second. Good. So let's calculate now the AS, the surface area. It will be pi into the diameter into L. This is the surface area. Now the volume will be again pi into the square root of the diameter by 4 into L. This is the volume. And then I can find the mass will be the density into volume. So I should add the density here. In density will be 7832, and the mass will be density into volume. This is the mass, and I should add the CV here. CV value is given in the question. It is CP. Okay, CP is same as CV. These are incompressible substances, therefore they have the same value for the C. Here 434. This is the CV value. Okay, so I can calculate now tau. Tau will be mass into CV divided by H value into AS. Okay, so if I convert it into general, so you can see the values good. So you see, it is 1062 seconds. Okay, 1062 seconds. Tau is seconds. So what does it mean? It means that 3 times tau is required for oven to increase temperature of steel rod, wait my friend, to 95% of T infinity. Okay. So 3 times tau is required for oven to increase temperature of steel rod to 95% of T infinity. Okay. So if you know T infinity value, to reach that T infinity value, you need 3 tau. This tau is very large. You see, this is very large because these are steel rods. They are very large steel rods. But for thermocouple, if you have a thermocouple, tau is very small. It is microseconds. Okay. Therefore, you should understand what is time constant. Yes, Fişrat.
İlk mən burada tau necə tapdırmam?
Tau is M into CV into by H into AS. We calculate M, we calculate CV, we know H, and we calculate AS. Okay, then we know the tau, and now the time is to calculate the infinity. Okay, how do you calculate the infinity? I will write everything in a good form, so you will have Ts will be equal to Ts initial minus T infinity exponential of T by tau plus T infinity. I need T infinity, so I can write it as Ts minus Ts initial. This one will be to the left part of the equation, e to the power of tau. This is the left, and you will have T infinity minus T infinity e to the power of T by tau. This is the right part, so this one has go to the left part. So if I take the Ts, it will be 1 to the power of e to the power of T by tau, and this one, false, this one is false, sorry. So I can write this one as T infinity outside of the brackets, you know this stuff. So T infinity outside of the brackets, negative e by tau, and then I can find T infinity will be equal to Ts minus Ts initial into e to the power of T by tau divided by 1 minus e to the power of T by tau. Okay, this will be the equation for T infinity. Let's solve it and find T infinity and finish this problem. Okay, so let me go back to Excel. So T infinity, first I should find exponential of T by tau, the exponential of negative T by tau. Let's find it. So it will be exponential of negative, time is there. You should use seconds, okay? Be careful, not minutes. Then tau. This is the exponential. So let's write it now. Ts minus Ts initial to the exponential of e by t tau divided by 1 minus this one. So it will be, this part is T infinity. We are finding it. It will be first the upstairs Ts minus Ts initial times this exponential term. This is the upstairs. We have finished. Now the downstairs, 1 minus exponential of this one. Okay. This is the temperature of the oven. So you need this temperature inside the oven, 1000 degrees Celsius, to increase the temperature of the steel rods from 20 degrees Celsius to 450 degrees Celsius in a time of 10 minutes. Okay, it's very easy example, and you can plot its graph also, how the temperature changes with respect to time. We will plot it at the end if we have time. Okay. Do you have any question? No questions? Good. So let's see how much time we have. 45 minutes. Okay. Okay, let's plot it because we have time for this one. Plot it. Okay, let's plot it. Plot this versus time. So if I go back to Excel, what I want is that Ts, this one, versus time, seconds. Okay, I will change. I will add another column here. Right, let's add it. Insert. Let's make it small. This time will be variable time. Okay, I will change this time and to get the value of Ts. Okay, so let me do it. But you will have similar exercise for this one. Okay, so therefore be careful. If you have questions, ask it now. Okay, so now I will get Ts variable. Okay, so I get time variable as 0. Okay, I'm trying to get what is the temperature at the beginning of the process. I know it is 20 degrees Celsius, but I will plot it. Okay, so Ts variable will be equal to, what's the function? Ts initial 20 degrees Celsius minus T infinity, which is 1016, okay, multiplied with exponential of e to the power of exponential of negative. Now I will use this variable time divided by, there is the term here, tau. The tau is the same tau, okay, and the close the brackets plus T infinity, this one. You see 20 degrees Celsius. So if I change the time, let's change it and see, after 10 seconds, it is 29. After 50 seconds, it is 56, 65. After 600 seconds, it's 450 degrees Celsius. You see, so I can get now the change of the temperature of the steel rods with respect to time. So if I use 3 time constant, so 3 time constant multiplied with the tau. Okay. After this one, you get 966. It's almost 95% of this one. Okay. So you understand the stuff. So now I will plot the graph of it. So let's plot it. So first the time is 0. I increase the time as, let's say, how many seconds? 500 seconds. 400 seconds. This one will be plus 400 seconds. And then for amount of, yes, for this amount of time, I will plot the graph of Ts variable. Okay. So I do the same stuff for this one, and you will get error. Why do you get error? So you see, if I move on to next cell, this one updates the values of D3, which is the S initial, it is empty, P3, which is empty, P3 is very, T infinity, which is empty, H3, again empty, no, it is here, N3, where is N3? N3 is empty, you see, P3, again empty. Now what will I do now is that I will make D2 as $. So F4, press F4, let me add it here. So you will press F4 to make cell constant. Okay. So now I will press F4 to make D2, which one? This one, okay, D2 constant. I don't want to change because I want only the time to be variable, okay. Then P2, what is P2? This is T infinity. I want also to be constant. Then H2, what is H2? The time. It should be variable, therefore I don't touch it. N2, which is the tau, again it should be constant. And the P2, where is the P2? T infinity, it should be constant too. You see, only variable is this one. And now if I update cells, you see the temperature of the steel rods. And if I plot the graph of it, insert, I can plot it. Okay, now I can add the data, select the data. So first let's make it smaller because I should see the chart. So select data. So I'm selecting for the series name as TS versus time. For X values, I will select the time. And for Y values, I will select the temperature. Okay, good. If I click OK, then OK, I can make it larger. Okay, it is famous exponential curve. So after 3 time constant is this one, 3 times this one. So let's write it here, 3 tau. It will be 3 times this one. Okay, around here, you see the curve almost becomes constant. It doesn't change anymore. 95%. This is 95% rule. There is one more exact, which is 4 tau, which is 99%, but we don't need it. 95%, okay, it is most of the time we use 95%, and therefore you have this chart, the temperature of the steel rod versus time. Okay, good. If I go back to the slide, so we have finished the transient conduction part.